Look at the sheer physical density of a modern processor. Hardware speeds are constantly changing, architectures are evolving, and clock speeds fluctuate. So how do we objectively prove that one algorithm is actually faster than another, regardless of the physical machine running it? The answer requires us to completely ignore the hardware. We evaluate software using a mathematical framework called asymptotic analysis. Instead of measuring seconds or megabytes, we evaluate an algorithm strictly on how its resource demands scale as the input size, which we denote as n, approaches infinity. We track two specific resources: processing time and memory space. We translate code directly into mathematical models. This table breaks down a for loop, counting precise mechanical steps based on an input of size n. Multiplying a single step by n iterations gives the worst-case scenario. The math confirms a linear loop is always O of n. This chart visualizes that exact concept through big O notation. Big O mathematically defines the guaranteed upper bound of an algorithm's scaling behavior. The execution time, f of n, will always remain at or below the boundary line of c times g of n. Mastering this mathematical abstraction allows engineers to accurately predict software performance before writing a single line of code, and eventually weaponize memory to bypass exponential time limits. We build our analytical model by examining visible loop mechanics, specifically straightforward iterative brute force algorithms. This diagram maps out selection sort. Its objective is sequential. Find the smallest element and place it in its correct position, starting at round 0. The outer loop, index I, tracks the round. The inner loop, index J, scans for the minimum value. Moving to round 1, the swapping mechanism takes action. Each inner loop pass locks one sorted element, shrinking the unsorted section. This creates a descending arithmetic progression, n plus n minus 1 plus n minus 2. Resolving this formula yields a quadratic function, simplifying to exactly O of n squared. This in-place sorting requires many mechanical steps, making it computationally expensive in time. But because it requires no extra data structures, it uses almost zero extra memory. This is our brute force baseline, an O of n squared time complexity and O of 1 space complexity. We can achieve a sorted array with a different mechanic. Insertion sort is an alternative brute force method, shifting elements rather than strictly selecting the minimum. The intuition for this algorithm is exactly how a person sorts playing cards, picking up one card and sliding it into the correct sequential spot. Looking at this diagram for insertion sort, the physical swapping mechanic operates differently. The inner loop index J decrements gradually, taking a specific element and sliding it backwards until it hits its correct sorted position. Even though the physical swap is different, this pseudocode shows the architecture still relies on two nested loops updating linearly. The mathematical proof confirms this identical nested architecture forces the algorithm into the exact same quadratic complexity. Analyzing these visible, iterative loops is straightforward arithmetic. But to measure advanced algorithms, we must learn to uncover computational costs hidden completely out of sight within self-referencing functions. This leads us to divide and conquer algorithms. Here, standard loops are replaced by recursive function calls that break a problem down into progressively smaller, identical pieces. This creates a new analytical challenge. We can no longer count visible code lines. The total computational cost is now completely hidden inside layers of nested subproblems. To calculate that hidden cost, we use the recurrence relation formula. This foundational mathematical tool expresses the runtime of recursive functions. To solve it, we rely on the iterative method as our primary algebraic technique for unpacking these relations. The iterative method requires taking the initial recurrence formula and repeatedly substituting the value of n back into the equation itself until a clear pattern emerges. Forcing hidden recursive calls into the open mathematically is the only way to prove if an algorithm scales logarithmically or hits an exponential wall. Applying the iterative method to binary search, we start with its equation, t of n equals t of n over 2 plus c. We execute substitutions, replacing n with n over 2, generalizing the pattern across k iterations to t of n over 2 to the k plus kc. The recursion terminates when problem size reduces to 1. Setting n over 2 to the k to 1 executes a final algebraic conversion, proving k equals the base 2 logarithm of n. Substituting k back eliminates the recurrence entirely. revealing the algorithm's definitive, proven upper bound, O of log n. The iterative method provides precise mathematical proof of how a recursive algorithm shrinks a vast search space to a fraction of a second. While divide and conquer can split problems efficiently, poorly structured recursion carries a massive risk. Naive algorithms often duplicate operations while attempting to divide them. The textbook example of this failure is the naive recursive approach to calculating the Fibonacci sequence, which results in a catastrophic exponential time complexity. This diagram illustrates the call stack required to calculate the fifth number in the sequence. The execution tree instantly explodes outward. The fatal flaw is visible. Identical subproblems, like Fibonacci of 3 and 2, are recalculated from scratch across multiple different branches. We solve this using dynamic programming. It represents the ultimate engineering trade-off, willingly sacrificing memory space to buy computational speed. The methodology solves the problem from the bottom up. We permanently store the answers to subproblems in an array as we go, ensuring the system never calculates the exact same subproblem twice. Watch this structural shift. By storing the results, that massive redundant exponential tree instantly collapses into a highly efficient linear one-dimensional array. Analyzing the updated dynamic programming code, the math reflects this shift. A linear for loop replaces the recursive tree. The trade-off is clear. Space complexity increases to O of n for the new array, but time complexity collapses drastically to a linear O of n runtime. Optimization is a matter of resource management, mathematically balancing the budget between processing time and memory storage to achieve maximum performance.